Welcome back everyone. In this module we will discuss about overview of semiconductors. So solids are classified into three types. One is conductor, another one is insulator, and third one is a semiconductor. So what is conductor? Conductor, it is a material or object that permits an electric current to flow through it easily. That means a conductor is a substance in which the energy gap, we know the bottom band which is completely filled with electrons is called the valence band, and the top band which is completely empty is called the conduction band. So in metal or in conductor, what happens? The energy band gap, which is the separation between the conduction band and the valence band, is zero, because this conduction band and valence band, they are overlapping in conductors. Okay, what are the examples of the conductors? We have metal wires, cables, rods, tubes, bus bars, etc. Okay, now what is the electrical property of a conductor? As we told that this band gap represented by Eg, it equals to 0 in a conductor, or a few times of kT. K is the Boltzmann constant and capital T is the absolute temperature in Kelvin. A large number of electrons that will be released from the bound state. Bound state means in this valence band. This valence band, it is completely filled with electrons. So in valence band, these electrons are bound to their constituent atoms. So in metal, a large number of electrons are released from this valence band and they move to the conduction band and they become free electrons there. These free electrons are only available for conduction. A large number of free electrons, they result in a large current with a small applied voltage across a conductor. What is the value of resistivity for a conductor? Obviously, it will be very less since the conductivity is high. It is 10 to the power minus 6 to 10 to the power minus 8. Metals are good conductors since they have partly filled conduction bands giving a large free electrons. Conduction and valence band, they overlap in metals, means that the electrons may move to a higher state with little or no additional energy imparted. So in this valence band that is completely filled with electrons, what happens in metals? Some of the electrons, when they move from this valence band to conduction band, they require little or no additional energy. Okay, in a metal, the valence band may extend into the conduction band itself, as the valence band and conduction band both are overlapping. Okay, now there is no forbidden gap since it is overlapping, so Eg equals to 0. And if we apply some electric field, the electrons will acquire additional energy and they move to the higher state. Okay, electrons are there in the valence band, so if we apply some external energy or electric field, they will gain energy from that and they will jump to the conduction band. But in that case, in the case of metal, we need to apply very small amount of energy. Now coming to the insulators. What is insulator? Insulators, they offer very large resistance to the flow of electric current. So an insulator is a substance for which this energy band gap Eg, it is 6 electron volt or more. And insulator is a material, it has low level of conductivity under an applied voltage. Okay, what are the examples of the insulators? We have diamond, glass, mica, quartz, etc. So what are the properties of the insulator? Electrons that are present in this valence band at a very large amount, so we need to apply a very large amount of energy to transfer an electron from this valence band to the conduction band. So these insulators are bad conductors of electricity, and the resistivity of this insulator, it is very high, 10 to the power 10 to 10 to the power 20 ohm meter. As we can see, this energy gap in case of this insulator is quite high. Okay, so as a result, this valence band, the electrons, they are bound to their constituent atoms and they can't be made easily mobile. We need to apply a large amount of energy, and after consuming that energy, these electrons will be able to jump in the conduction band and they become free electrons there. Okay, this is the scenario in case of the insulators. Now what happens in case of the semiconductor? So the semiconductor is a solid and it has the electrical conductivity in that of the metal and the insulator. And the best property of the semiconductor is we can actually tune the band gap of the semiconductor and use it as per our required application. So in the case of the semiconductor, the energy band gap is 1 electron volt. Okay, silicon, germanium, they are examples of the semiconductor. Silicon is most widely used. Okay, so what is the electrical property of the semiconductors? At 0 Kelvin, when capital T equals to 0 Kelvin, this valence band is completely filled and this conduction band is empty. As we keep on increasing the temperature, suppose now we are increasing temperature from 0 Kelvin to 300 Kelvin at room temperature. So some of the electrons which are there in the valence band, they will acquire enough energy and they will jump to the conduction band. So at T equals to 0 Kelvin, semiconductor behaves as an insulator. Okay. Now as we keep on increasing the temperature, these electrons are jumping from this valence band to conduction band, and as more number of electrons they start getting available in the conduction band, what will happen? The conductivity will increase. Conductivity increases means resistance will decrease, and that is why these semiconductors are said to have negative temperature coefficient of resistance. Means as we keep on increasing the negative temperature coefficient of resistance means as we keep on increasing the temperature, with increasing temperature my resistance will decrease. That is why it is called negative temperature coefficient of resistance. Okay, now the value of resistivity in semiconductor, it will range between 10 to the power minus 3 to 10 to the power 7. That is, it is in between your conductor and insulator, and the conductivity also for the semiconductor is in between that of the conductor and insulator. Now, semiconductors are broadly classified into two types. One is intrinsic semiconductor, another one is the extrinsic semiconductor. Now, what is intrinsic semiconductor? Intrinsic semiconductors are pure semiconductors. They are 99.99% pure semiconductor. We don't need to add any external impurity to such semiconductors. For example, silicon, germanium, they are intrinsic semiconductor. Okay. Now, in the charge carrier concentration means the number of charge carrier per unit volume. So in case of germanium, the intrinsic carrier concentration, which is represented by Ni, it is 2.5 into 10 to the power 13 atoms per centimeter cube, and for silicon it is 1.5 into 10 to the power 10 atoms per centimeter cube. And in case of the intrinsic semiconductor, the number of electrons are equals to number of holes. Okay, so this is what you are observing here. This is the energy band diagram of an intrinsic semiconductor. So this is my valence band. This is the top level of the valence band, which is represented as EV, and this is my conduction band. This is the bottom of the conduction band, which is represented as EC. And for an intrinsic semiconductor, the Fermi level EF will lie at the middle of the energy band gap. What is Fermi level? It is the maximum energy level that is occupied by the electrons at 0 Kelvin. Okay, and here in this figure it is shown the crystal structure of an intrinsic silicon. So in silicon, what happens? In outermost shell they have 4 valence electrons. Okay, so those outermost shell electrons, they can make covalent bonds with the nearest neighboring atoms. Okay, so in this figure the crystal structure of the intrinsic silicon is shown here. Now what happens, we will see in the next slide. Like, you can take either silicon or germanium, both are having 4 valence electrons in their outermost shell. So this is the crystal structure of the germanium. So each silicon or germanium atom, they are connected with another silicon or germanium atom through a covalent bond. This is one germanium atom, this is one germanium atom, this is one germanium atom. So their outermost shell, they have 4 valence electrons. So each silicon or germanium atom is connected with another silicon or germanium atom by this covalent bond. This is the covalent bond. So these are 4 valence electrons. So these 4 valence electron is shared by nearest neighboring another silicon or germanium atom. Okay, so what is happening when the temperature is 0 Kelvin at valence band? All the electrons are tightly bound. Okay, because as no electrons are available in the conduction band, so the semiconductor will be having very low conductivity. Okay, now if you keep on increasing the temperature from 0 Kelvin to 300 Kelvin, what will happen? These covalent bonds, some of the electrons, which are tightly bound in the valence band, they will acquire enough energy and they will break these covalent bonds. These covalent bonds, they will be able to break. Okay, now suppose an electron was here. Okay, it is capable of breaking. Sorry, focus on this electron. Initially this electron was here. So as we keep on applying the thermal energy from outside, this electron is capable of breaking the covalent bond, and now it has it is able to move to the conduction band, and now it has become the free electron. So once this electron leaves its own position, a vacant position will be created here. So this vacant position is called the hole. Okay, now another electron, they will come and occupy this vacant position. Then again this electron will become free electron, then another electron will come. So this is a process which continues on and on, and it is creating the movement of the electrons. Okay, if the electron movement in is this side, the whole movement will be to the opposite side of the electrons. Okay, now coming to the extrinsic semiconductor. Extrinsic semiconductor means we have an intrinsic semiconductor. When we add or when we dope, there is a word called doping. When we dope the intrinsic semiconductor with impurity atoms, then we get the extrinsic semiconductors. Okay, and the usual level of doping in the range of 1 impurity atom per 10 to the power 6 to 10 to the power 9 silicon atoms. So extrinsic semiconductors, how do we get? We dope the intrinsic semiconductor with some impurity atoms. So extrinsic semiconductors are classified into p type and n type. We will see what are these semiconductors. So if it is, how do we get an n-type extrinsic semiconductor? Suppose I have a silicon intrinsic semiconductor. When I dope this silicon with pentavalent impurities. Pentavalent impurities means atoms that are having 5 valence electrons in their outermost shell. That is called pentavalent impurities. Okay, so what are those pentavalent impurities? Arsenic, antimony, phosphorus. Those are my pentavalent impurities. Okay, so suppose I am doping silicon with phosphorus. So silicon has 4 valence electrons in their outermost shell, and phosphorus, they are having 5 valence electrons in their outermost shell. So 4 covalent bonds will be created. 4 out of the 5, because silicon, they are having 4 valence electrons in their outermost shell, no, and phosphorus, they are having 5 valence electrons in their outermost shell. Okay, so 4 covalent bonds will be created. Okay, and the fifth electron will be free. 4 out of the 5 electrons will participate in creating the covalent bond, and the fifth electron will be free, and this free electron will take part in the conduction, and the energy that is required to remove this or to make free this fifth electron is very less. Okay, now phosphorus, what they have 5 valence electrons, so they can donate the electron to silicon. Okay, that is why it is called donor atom. Now what is p type semiconductor? When I dope the intrinsic silicon with trivalent impurities, that means atoms that are having 3 valence electrons in their outermost shell. For example, aluminium, boron, gallium, we get p-type semiconductor. Suppose I am doping intrinsic silicon with boron. Okay, so what will happen? Here, three covalent bond will be created, and the vacancy will exist in the fourth bond. Okay. Now, once the vacancy is created, that means once a hole exists, so it will be the energy that an electron will require to occupy that vacant position in this case will be very less. Okay. So this I already explained how we dope the silicon with phosphorus. Phosphorus, this is what you are observing. This is the crystal structure of the silicon. We are doping the silicon with the phosphorus. So phosphorus is having 5 valence electrons. So 4 of the 5 valence electrons, they will occupy the covalent bonds. And this fifth electron, this is the fifth electron. So this fifth electron will be free and it will be available as a carrier of current. And this phosphorus, since they are having extra electron, they can donate excess electron to the silicon. So that is why they are called donor atom. Now, how do we get the p-type semiconductor? When we dope the silicon with trivalent impurities like boron. Okay, so boron has, or boron or aluminium. Okay, so this aluminium is having 3 valence electrons. Okay, so the 3 of the covalent bonds associated with this aluminium atom can be filled, and vacancy will exist in the fourth bond, and it will create a hole. So once a hole is created, some nearest neighboring electron, they will come and occupy the position. So in this case, the energy that is required is very less.